Awesome. Thank you so much. Well, hello, everybody, and welcome. My name is Leslie Holland. I'm an assistant professor and extension specialist in fruit crop pathology here at UW Madison. And on behalf of UW Madison Extension and University of Minnesota Extension, we welcome you to our pesticide selection and resistance management for your Vineyard webinar series. So today we'll be discussing specifically resistance management, understanding IRAC and FRAC codes. So I'm sure you've heard us use some of this language before, but we're going to do a bit of a deeper dive into that today. Before I hand things over to our first speaker, Christelle Guedot, just some housekeeping things. We ask that everyone stay muted throughout the duration of the presentation, and then you can enter your questions into the chat. During the presentation, after the presentation, we'll spend some time answering your questions. And we also want to advertise our next presentation, I believe in April, on herbicide selection as well. And that'll be Annie Claude from the University of Minnesota. So that will be occurring next month. And you can register for these webinars at our website. I will put the link in the chat. And if you'd like to watch some of the previous webinars we've had on grapes or apple, dealing with fungicides and other pesticides, those can be viewed at our YouTube channel, which is also in the chat. So with that, I will turn it over to our first speaker, Dr. Christelle Guedot.
Hello, everyone. Thank you, Leslie. I will start sharing my screen and start talking to you. Is that going? Okay, can you see my screen now?
Yep, perfect.
Okay, all right. So, well, thank you, everyone, for being here today. And my name is Christelle Guedot. I'm the fruit crop entomologist and extension specialist. I work with all the fruit crops in Wisconsin, and I'm happy to talk to you today about resistance management and understanding IRAC and FRAC codes. So the talk will be divided into two parts, kind of. I will talk at the beginning about really the principles of resistance management and resistance. How does resistance happen? And then Leslie Holland, who introduced herself just before, will dive deeper into the FRAC codes and how would you apply this resistance management strategies to a fungicide rotation. So that's kind of the outline of this, this presentation that we'll go through. So the first, hold on, I'm having an issue with moving stuff around so I don't see myself so much. Okay, so the first question that I'll start us with is, what is resistance? And that's really at the core of what we're going to be talking about today. And the resistance is really a genetically controlled decrease in the susceptibility of a population. So it could be an insect population, it could be a weed population, it could be a fungi population, to the control measure that is applied. And so that can come in the form of pesticide resistance, but it also can be in the form of adaptation to pest-resistant crop varieties, or the adaptation to even a crop rotation. And so this translates overall, this resistance, into a failure to achieve the expected level of control. So you have an expectation and you're not able to meet that expectation with the control measure you're using. And when we talk about pesticide resistance, it's very important to think about it all the time when we think, especially, and that's what we'll talk about for those pesticides, is it's happening. It's really happening. At all levels. It's happening in the weed world, in the plant disease world, and in the insect world. And we have fewer and fewer new chemistries. And so we really have to start thinking all the time when we apply pesticides on how we can delay or prevent resistance from happening. So here are some numbers about what resistance has been yet identified, and it should say resistance to pesticides. There's over 500 insects and mite species that are resistant to at least one class of insecticide. There's also at least 17 insect species that are resistant to all major classes of insecticides. So we are struggling, and spider mites are one big example, where they're resistant to all the major classes of insecticides. So it's very important to think about that and how can we deal with that resistance that has happened already. There's over 270 weed species that have shown resistance and over 150 plant diseases that have shown resistance. And every major agricultural crop has been reported to have at least one or more resistant pests. So not only is it from the insect, weed, or disease, but it's also the agricultural crops have all reported resistance to those pests, with those pests. And pests can also develop resistance to things like insecticidal soaps, BT, Bacillus thuringiensis, a bacterium, and even pheromone mating disruption. So we have to really think about it as not just a pesticide resistance, but also on that standpoint of other aspects of pest management. Why should we care about resistance? Of course, there's this loss of multi-site chemistries that really is leading to the reliance on single-site chemistries. And by that, I mean broad spectrum pesticides that will have multiple multi-site chemistry potentially versus single-site chemistries that will be more narrow. And that will be very important when we talk about that in a little bit. There's not a lot of products that are coming in the pipeline. As you all know, we haven't seen a lot of very new products. And when there are new products, they very often have either similar or even the same mode of action than the existing products we have. And we see that in all the different aspects of the pesticides. Also, from a registrant standpoint, the discovery and registration of new product cost between $200 to $350 million for a single product. And the time to develop those new products is in the range of 8 to 15 years. So it's very important to maintain the current products we have in the market because we rely on those tools and we are not coming up with new tools as often as we wish we could. And that's, we have limitations in coming up with new products. But I want to take a step back and let people know that really not all control failures. So when we have a failure in the control and we're not getting the expected outcome from a control strategy, doesn't mean that you have resistance per se. And sometimes we're quick at jumping to, oh, this pest is becoming resistant, when there are things that growers can do to really think about what could be another problem of why that control failed at providing the control that was expected. So one common one would be calibration error or mixing error, using an inappropriate product, a product that doesn't have as much efficacy as you thought they would have, or mixed up the product that you've been using. The use of outdated products, some of those products can sit in the shed for several years, we're not using them, and then they're outdated and they don't have the efficacy that we would expect. There's also reinfestation following application. You can think about Japanese beetle, for example. If you apply an insecticide and then you come back with more beetles that are moving in, well, they could just be moving in and not that you failed to control with the insecticide you use the population that was there. And it could be others, other things that we have not thought about that could also lead to that failure in control measure, but that is not associated with resistance. So how does resistance happen? Resistance, because it's an inheritable genetic characteristic, that means that the genes that are controlling the resistance mechanisms are naturally occurring in the pest population. They are at very low initial frequencies for the most part prior to a pesticide application, but they are present in the gene pool of the population. And I'll show you that in a little bit. And so what happens is often it comes that that genetic basis that's already there comes from mutations that have made a pest less sensitive to a pesticide. And it's often retained at a very low level as what we would call a heterozygote phenotype. And so a phenotype is what you see, what is expressed from that genotype. And I'll show you a little bit more of what we're meaning by that. And so we would call them, these individuals that are resistant, we would call them R, and the individuals that are susceptible would be S. And so I'm going to show you a little bit what it would look like in the field if you have those populations. So when we talk about those resistant genes occurring naturally at low frequency, we're talking about 10 to the power of -6 or -8. So that's a very, very, very low frequency that you really wouldn't see, because you expect that when you kill insects, for example, you're not going to kill 100% with the control method that you're using. There's always some that are surviving, but they're surviving because you didn't reach them, or they're surviving because they have that low frequency of resistant genes there. And so the pesticide that kills the susceptible individuals is what you see, but by doing that, they actually select those with the mutation that have those resistant genes, because those survive, and the more of those that survive, the more they're going to be able to pass on those genes to the next generation. So in the end, you have proportionally more insects with the R genes that will survive. They will then reproduce. They pass on their R genes to their offsprings when they're exposed to the toxin more often than insects with only the S genes. So if you're looking at it from really a Mendelian genetics, what you would have in a population, and I'll show you some graphics after that, you would have a population on the left-hand side, the RR population, that have the two alleles, we call that code for that gene, that are resistant. So that's a fully resistant individual. You have an SS on the right-hand side that are fully susceptible. They have the two alleles for that gene that are susceptible. And then in the middle of that, you have what we call the heterozygotes. And those are R and S. And so there's a lot of also conversation we're not going to have today about whether the R is dominant or recessive, but we're not going to go into that. We're going to assume here that that's kind of a dominant trait. And so I want to acknowledge here that all the graphics I'm going to show you here were made by Russ Groves here at UW Madison, the vegetable entomologist. So let's say we understand this part of the three possible genotypes that we would have in the population. And you start with this first generation, again, at this very, very low frequency of that heterozygote. So you have that little blue allele here in this population of fully susceptible population outside of that. So you're spraying your insecticide and you're killing all of the susceptible, but the resistant one is one that will stick around, reproduce, and then in the next generation, you have a little bit more of that, that resistant gene that's showing up. And some of those individuals that you can see, for example, this one here, this represents a moth, or this one back here, that are fully resistant. They have the two alleles, they're completely resistant to this strategy. And as the generations continue, where generation 8 to 13, you have more and more of those resistant individuals that are able to survive this pesticide application, to the point that you're going to have fewer and fewer of the susceptible individuals, and really coming up with only very, very few individuals. So eventually the population is made up of resistant individual and not so much susceptible. And that's the problem. That's really what we're talking about, is we're selecting those resistant phenotype, because by killing all the susceptible ones, we're leaving behind the resistant ones. And so they reproduce and pass on their genes. So what factors influence how fast resistance can develop? There are a lot of factors that can dictate some of that. There's of course the genetic factor, the frequency of the R genes in the original population, the fitness of the R individuals, how much they can reproduce, etc. The inheritance of the resistance, how easily is it passed on? Is it dominant or recessive, etc. So that's the genetic factors. There's also biological and environmental factors that will impact how fast that can develop. The population biology of an insect species, for example, is very important, and that will apply for the other pests as well. But what's their reproductive rate, their mortality rate, the number of generations per year? If you have one generation per year, they're going to be less likely to develop resistance because they only hit one time even if you repeated the exposure, there's only one generation. Whereas if you have lots of generation, they could be exposed multiple times throughout that cycle. And so selecting more and more of those resistant individuals within 1 year. The dispersal rates and the distances that they can travel, the host range that they are, if they go to different hosts, then there can be reservoirs outside that would bring in potentially more susceptible populations. And the short generation time is also going to play a role there. But there also are operational factors. And those are the ones that exert the selection pressure and are under human control. And by that, I mean the pesticide use and the crop production practices are some that are very important. And that's where we have a control over and what we can do. We actually don't control the biological and environmental factors that are at play here or the genetic factors, but the operational factors is where we can play a role in trying to delay or prevent resistance from happening. And so those operational factors would include the pesticide use practices. Really, that's what we're looking at. And so when you're choosing a pesticide, choosing pesticides that have a shorter residual activity, so there's less exposure, would help prevent resistance. I'll talk about that in a minute, but using pesticides that are known to have no or negative cross resistance would also help in delay resistance. And we'll talk about cross resistance in a little bit. The more selective a pesticide is in the target sites that it's going to be, we'll talk about that too, but it will be targeting, are going to be more prone to resistance because they're using only one target site. And then, of course, the method of application and even coverage may kill all the susceptible individual, but may allow the heterozygote that have the resistant gene to escape. Spot treating, hotspots, that's thought as minimizing selection and providing refugia. And so that's something that we're not going to talk about, but refugia is an important part in providing an area that would provide some of those susceptible individuals to survive outside of the crop. And that's being done in some crops where there's intense resistance, is allowing some refugia on the side. So where you have a population that continues to have that susceptible trait. And of course, the frequency of application, the more frequently you apply, the more likely you are to exert that selection pressure on the resistant individual. So another way to look at this is looking from this slide that I got from a webinar that I was looking at from the University of Amherst, Massachusetts, Amherst, and Maine, and Northeastern Stayer. And that's a slide from their presentation, but at the bottom you have the low risk, and at the top you have high risk. So what's at lower risk is alternated application of different pesticides versus repeated application of the same pesticide. And that's what Leslie will talk about in more detail. Spraying based on an economic threshold is going to help delay resistance as opposed to using a calendar-based spray. Annual crop rotation can help in preventing that compared to a continuous crop. And then spot and perimeter treatment as opposed to treating a whole field so that you maintain some kind of that susceptible population in your field. So again, this is kind of an introduction. Why we're here is to understand modes of actions. And so what we have is we have those alleles when we're talking about the two circles on a moth, there's two alleles for genes. And the alleles that are conferring resistance to a pesticide can actually confer, I don't know how we say that, some level of resistance to other insecticides to which the pest population has never been exposed. And that's what we call cross resistance. So you've never been exposed to that, but because it's following kind of the same mode of action, and we'll talk about that, you get cross resistance to other products. It's where that target site may be. In other words, the resistance to several pesticides is resulting from a single resistance mechanism. And so that's the thing, is that if you have one mechanism of resistance, it can then apply to several pesticides. And so that cross-resistance is most often based on the mode of action of the pesticides. And of course, the chemical structure of the pesticide is going to define what its target site is going to be and what its mode of action is going to be at that target site. And that's when we come into the IRAC and FRAC and HRAC groups. We're really looking at where is that resistance happening, what is the mode of action of those pesticides, and what is the target site of those pesticides. And that's what helps us, once we understand that, go back to if they have the same mode of action and the same target site, then they're likely to have the same kind of mechanism of resistance that's going to apply to those different pesticides. So here, what I want to show you, and we'll go into that in the next slide, but if you look at this caterpillar here, what you see are those different bubbles, and those are defining different target sites. So we have some that target the growth and the development. That will be your insect growth regulators, for example. You have nerve and muscle targets. That's the majority of the pesticides we're using right now. We have a midgut target, so we have a respiration target. So that's the target site where within the pest are they targeting to kill that insect in this case. And that's what defines that target site and how those pesticides get to the target site and how they affect the target site physiologically. That led to this creation of those committees to provide pesticide codes. And so those committees were really created to help classify those pesticides based on their mode of actions and their target site, so that the idea is to delay or prevent resistance from happening. So that's really the basis for resistance management, and to give tools to the users on how to easily see that on the label. So that's kind of the goal of those. There's a lot more to it, but really the bottom line of what we're going to talk about today is how can you use those that have been created by the IRAC group, the Insecticide Resistance Action Committee, or the FRAC group, that is the Fungicide Resistant Action Committee, or the HRAC group, the Herbicide Resistant Action Committee. And that's what we'll talk about. So they classified all the pesticides, and there's a lot of classification in insects. That's why Leslie and I decided it would be better to give you the example of what it happens in the fungicide world. But we have all of those groups, and all pesticide labels include a code now. And you can see it here on this Altacore, or here on this Indar. There's a group for those insecticides and a group for the fungicide. And that helps you look at this and see that if you're switching from Altacore, for example, to Exerol or Verdeprin, you're still within the group 28. And so this is very important, because that helps you realize that if you weren't sure, quickly you can tell, oh, these have the same mode of action, so they're not going to help me in resistance management. And there are in all the labels the information on what you should do and have to do to prevent resistance. So, and Leslie will talk about that again, but all labels will have a resistance management statement, and it will tell you how many applications per year for each of your crop and how many applications of the same group of pesticide you can have to delay or prevent resistance. And so here you have an example of the IPM fruit pest management guide with the table that says for each of those pesticides, so in this case it's fungicide, what are the active ingredients and what are the FRAC groups, so that you can go back to that when you're making those decisions to make sure that you rotate amongst those different chemistries. And so that's what then from the target sites that I just mentioned here, if you look within those bubbles underneath, for example, here, the nerve and muscle targets, so we're very specific at those targets, But now we have the group 1, that's our carbamates and organophosphates. We have our group 2 that are going to be the organochlorines and the phenylpyrazoles, et cetera, et cetera. So these have been grouped from the target site to the mode of action. And that's the group, in this case, for the insecticides. And so now I'm going to switch us to Leslie Holland. She's going to be continuing the rest of the presentation and diving deeper into those codes and how you would use them. Thank you, Leslie.
Excellent. Thank you, Christelle. That was a great introduction into the world of IRAC and even touching on FRAC a little bit in terms of how we talk about resistance management. So before I jump into some of the more fungicide-oriented sections, I just wanted to do a quick vocabulary and key to make life a little bit easier for me in my slides. So the first thing I really want to cover is looking at multi-site versus single site. And so sometimes we use these terms when we talk about fungicides, right? Kind of the lingo of fungicides or even insecticides at this point too. But really what a multi-site fungicide is something that affects multiple sites within that fungus, right? And these are, we call them relatively low risk fungicides because the ability of the fungus to overcome or become resistant to this particular type of fungicide is pretty low. Because if you have multiple versus single, it takes, a lot more time to get over 10 hurdles than it does to take over one hurdle, right? And so then that brings us to single site fungicides. And so these only affect a single site. And these are generally kind of coined or termed as at risk. And so they could be anywhere from medium to high risk fungicides. And again, that risk is higher because it's a lot easier for that particular fungus to overcome that fungicide's mode of action. And I put some examples here. Again, it's not an exhaustive list, but I'm sure you're familiar with some of the names that you see. Additionally, we think about premixture or kind of single active ingredient. So this is kind of another way we talk about fungicides. So when I say a single active ingredient, those are the fungicides that contain exactly that, one active ingredient. So, looking back above, that's like a Bound, Rally, that's a FRAC 11 and FRAC 3 respectively. That's a single active ingredient acting on the fungus. When we talk about a premixture, those are those fungicides that you're able to buy, right? That include usually two FRAC groups or maybe 3 FRAC groups for some premixtures. And so those contain a couple different modes of action. And examples of that are Ridimil Gold, Inspire Super, Luna Experience, Maravon, and Pristine. And I include this key down here because I'm going to be referring to some of the different diseases that we deal with in grape production. And I've put some abbreviations to make life a little bit easier. And MOA, of course, is going to define our mode of action. As Christelle already explained, these different IRAC, FRAC codes are used to distinguish these different pesticide groups based on their essential biochemical mode of action and the different pathways of these pests and pathogens. Next slide. Perfect, thank you. So Christelle kind of already went over this in terms of resistance in general. So just kind of thinking a bit more specifically about fungicide resistance development, highly susceptible varieties under very favorable environmental conditions. And of course, these two things alone aren't going to cause fungicide resistance, but it's how we use our fungicides or pesticides during this particular period of time. And so for fungi in particular, a lot of them really thrive in these kind of moderate to warm temperatures and really moist environments. So if you've got pretty high disease pressure and you're making your applications under these really kind of extreme conditions, that can be a bit conducive to that resistance development. Additionally, improper timing of fungicide application. This makes sense. If you're applying fungicides nowhere near the time that these fungal pathogens are sporulating and then dispersing, you're going to miss those target periods and maybe only apply to a fraction of the population and not really hit your target. So an important way to kind of stay on top of this is to really keep an eye on plant phenology in the field, right? Do your scouting, see where your grapes are at. And additionally, incorporating NUA is a really excellent tool to keep you on track with the plants in your particular city or region. And we have quite a few stations located in Wisconsin as well as Minnesota. Applications of fungicides after an epidemic. And so this is a really big issue because you're then exposing a very large population to that fungicide. And as Christelle really beautifully demonstrated earlier with the insects, when you're exposing that large of a population to something, some of those are going to survive and reproduce and continue to perpetuate that resistant gene in those offspring. And proper fungicide rate is another important thing. And so it's really important that you stick with the label rates that you see on that fungicide label. And we also tend to include those in our pest management books as well. So stick between those label rates. If it says between 16 and 20, stick between the 16 and 20 fluid ounces. You don't want to go on the low or high end or the beyond that range. And additionally, as Christelle emphasized, repeated use of the same chemistry, the same mode of action is a really quick recipe to get you to fungicide resistance.
Sorry, Leslie, I'm having a problem switching the slides. I don't know why.
Oh, no problem. Thank you. Okay. One back, please.
Oh, sorry.
Thank you. So the goal of resistance management, of course, is to delay or prevent its development, period. Resistance management guidelines are typically listed on your fungicide labels, and so you must follow those. There are regulations about how many applications you can make of a certain group in a growing season, and that comes in number of application, that also comes in the total quantity, whether that's ounces or pounds, how much you're able to use per season. And a lot of this is in effect to help prevent the onset of fungicide resistance. So really basic principles are minimizing selection, and you can do this by using alternative controls and management tactics. So all the way from cultural controls to other modes of action, of course. Thresholds are definitely an important thing to rely on, especially in terms of insects and insecticides, but also for some fungal pathogens where we have those numbers available. Additionally, using pesticides with negative or no cross resistance, and Christelle mentioned what cross resistance is, and there are some reported cases for some fungi as well. So I really like this idea of following the rules. And so I took this from a University of California book on the guidelines for resistance management, and it includes some of their other cropping systems that they have their rating scales for. But I like this because it's relatively easy to remember, and it spells out rules, which is even better. So the first R, right, is rotate between fungicides with different modes of action. And I'm not talking about waiting until you've depleted all of your 2.5 gallon jug of whatever your fungicide is and then switching. Rotations need to happen within the season, right? If we use one mode of action for 5 years and then switch, that's not rotation. And those habits are going to lead to fungicide resistance. So we've got to rotate within that season, different modes of action. Again, use those label rates. We tend to save that high end of the label rate in situations that we consider critical periods for disease control. So every crop is going to have critical periods to control certain diseases. And that's when you want to use that high end of the label rate. And under low disease pressure situations, you can use the lower end that's on that range. Again, limiting the total use of those single site mode of action fungicides, and then educating yourself on the different modes of actions that are available to you, the different rates and the performance. And so something like the Midwest Pest Management Guide, or if you're an organic grower, Cornell has an IPM guide for grapes. This is where you can find that performance information. It's really important to note that fungicide labels, insecticide labels, these labels do not say anything about the efficacy of those products. They simply state what crop it's registered on and what diseases or pest it's registered for. It states nothing about the efficacy. So use those guidebooks, right? There's certain chemistries that aren't going to work for powdery mildew that work really great for downy mildew. So know what you're spraying in terms of what your target is. And finally, that last, looking here for S, start a fungicide program with a multi-site or tank mixture to reduce the fungal population exposure to a single site mode of action, right? So start off your program strong without exposing your population to anything that would quicken that race to resistance. So jumping into some of the chemistries we have available. Now, I'm not going to be able to talk about every single FRAC group in chemistry that we have available to us in grape for disease control, but I want to highlight some of the maybe more common ones that we tend to use and that we tend to see recommended. So this first is going to be multi-site chemistry. So this is what we have a FRAC M. And so FRAC M, essentially that is that multi-site, right? That's what that M means. And so some chemistries I'm sure everyone is familiar with at this point: mancozeb, captan, xiram, copper, and sulfur. These are all chemistries that are considered at multiple sites where they're acting to prevent that fungus from really exploding. In terms of their efficacy, it depends on the chemistry. Mancozeb is a really great chemistry for quite a few diseases early in the season, from powdery to downy mildew to black rot, where Xyram is really great for black rot and has a little less efficacy for some of the others, right? And again, this information is in your pest management guides. In terms of that pre-harvest interval, they tend to be fairly long, a little bit longer than our traditional single site fungicides. And so I bring this up to say these tend to be really great tools earlier on in the season because that pre-harvest interval is so extensive. So you're going to have to be really mindful about using these the later you get into this season. It's just something to be mindful for. But again, check the label because it's quite variable from Captain to Mancozeb. Additionally, with that longer PHI, as I mentioned, it's not ideal for late season control. And as I emphasized earlier, these multi-site chemistries are relatively low risk for fungicide resistance development. But it's important to remember that low risk does not mean there's no risk, right? So still using these with good pesticide stewardship is of value. So mode of action, this is kind of, these particular fungicides act on respiration processes within different fungi. So the first is FRAC7, or sometimes we call them the SDHIs, right? Kind of getting back into this lingo that we use when talking about these codes. And so some examples of this are fungicides like Luna Privilege, Endura, and Aprobia. But there, of course, are others you can find in the guidebooks. And of course, you know where to find the numbers on the label too. These tend to be really good for powdery mildew control. And their PHI does tend to vary based on product, but kind of anywhere between 7 and 14 days. An important thing to keep in mind for FRAC7 fungicides is that we often find them in mixtures. So if you tend to buy things like Aprobia and Endura and use those, keep an eye out if you have anything like Maravon or Pristine, because those also contain a FRAC7. So it's really important to distinguish between those premixtures versus single active ingredient products that you're buying, because you could in fact be applying double the FRAC7 you thought you were, but it's really important to focus on those numbers on the label. And FRAC7s in general tend to be medium to high risk. There have been cases of resistance reported, but I would say probably more severely in that category, unfortunately, is our FRAC11 fungicides, or sometimes called our QOIs or strobilurins. And so examples of this would be Abound, Flint Extra, and Sovereign. And these are really excellent fungicides for both powdery mildew and black rot, and they're pretty good for downy mildew as well. Again, they've pretty much got a variable pre-harvest interval, but they are high risk for fungicide resistance. And I would say of all the FRAC groups we'll cover today, FRAC11 is one of the more high risk ones that we tend to be concerned about in our applications. But as you probably are aware, we use it quite a bit, and we tend to find it in a lot of different premixtures. So again, you are limited in the number of applications you can make with this FRAC group due to that really high risk of resistance. So keep an eye out when you're using those premixtures or your own mixtures that you're doing, how much FRAC11 you're actually using. A couple other mode of actions. These are specifically targeted towards cell wall biosynthesis. So right, just another way to kind of bring that fungus down. FRAC19 are these polyoxin kind of salts. I'm just listing also 5% as an example, but there are other products. They're pretty good for powdery mildew and botrytis, and they tend to have a low PHI, which is nice. In fact, also specifically is on the OMRI list, or so it's registered for organic production, but this is not true of all of the FRAC19 products. So again, you need to look for that OMRI insignia on the label. And these tend to be medium resistance risk for fungicide development, fungicide resistance development. FRAC40 is another group that we tend to see a fair amount of, and this includes fungicides like Revus and Forum. And the FRAC40 is really targeted towards our downy mildew control. PHI is roughly 14 days, but again, check the label. And we tend to see FRAC40 in a couple of these premixtures as well, that maybe our FRAC40s are targeted towards our downy mildew, and then a mixture might have a FRAC3 included to try and capture that powdery mildew element, since we tend to deal with both fungi within the same season. And these fungi tend to be low to medium risk. So another mode of action, another common group are FRAC3s or DMIs, and these are what we called our Sterol biosynthesis inhibitors. And so this is where they're interfering with a particular fungus. And we see these a lot relatively early in our fungicide programs, likely with our rallies and our Zevias and metals and things like that. They are really great for our black rot, which is an early season concern, as well as our powdery mildew. And again, PHI can be anywhere from 17 to 14 days. And again, like our FRAC 7s, like our FRAC 11s, we see a fair amount of these FRAC 3s in premixtures with other chemistries. So oftentimes we see a FRAC 3 fungicide mixed in a premixture with the 7 or an 11 or a 9. These are really common things we see. So kind of keeping that same rule for yourself in terms of keeping in mind how many times you're using a single FRAC group, because those premixtures can almost fool you if you're not paying attention, right? They are medium risk for fungicide resistance development. And in FRAC 7, in FRAC, back up 2 steps, as well as FRAC 3, we also see FRAC 17 as a Sterol biosynthesis fungicide. And so an example of this would be Elevate. And so Elevate, I think, is pretty okay for powdery mildew suppression, but it also is a really excellent product for botrytis. And we'll touch on that in a few slides. Finally, I'm just going to go over these last 2 modes of action. Again, this is not an exhaustive list. There are plenty of others, but I wanted to kind of focus on some of the more common numbers and chemistries that we likely encounter in our spray programs. FRAC 9, sometimes called AP fungicides. Examples are Vanguard and Scala. They're good for suppression of powdery mildew and good for botrytis control as well. That PHI is variable, check the label. And again, these fungicides are often found in premixtures again. So Inspire Super, that is a FRAC 3 and a FRAC 9 as an example. And they are medium risk for fungicide resistance development. FRAC 4 really is our Ridamil products. And so I think a lot of folks probably use Ridamil early in the season to really try and kick back any issues of downy mildew in those overwintering leaves or even on the vineyard floor. These do have quite a lengthy pre-harvest interval, which again is why we tend to see them more frequently used at the beginning of the season. And they can come in premixtures. So when you see things like Ridamil Gold, followed up by other things, those tend to be premixtures of Ridamil with another product, probably that would control something like powdery mildew. So these are oftentimes found not as solo, but as combination products. So something to keep in mind when you're purchasing these. And these are very high risk for fungicide resistance development. So I recommend that if you choose to use a product like this, if you've had downy mildew disease pressure in the previous season, use it sparingly. Because these are quite a high-risk group of fungicides. Oh, so I lied. Kind of moving into some of the other options you would have outside of our more conventional fungicides, I want to focus a little bit on our biologicals, because the FRAC group or FRAC numbers tend to be a little bit different for these. So we see BM, that's kind of the initialing or way that we phrase these different FRAC numbers for our biologicals. So the O1s are those that are plant extracts, and those that are microbial based are O2. And the M actually is trying to emphasize the fact that these tend to be multi-site. So they're biologicals, but they act on multiple sites as well. So an example for our plant extract base would be BLAD, which is, I think, Fracture is the name it's going under. And then for our O2s, we tend to have a ton of different products from Hallard, Double Nickel, Serenade, Stargus. And these tend to be things like Trichoderma, Bacillus, Pseudomonas, different fungal and bacterial microbes that are antagonistic towards our pathogens that we're trying to manage. Efficacy is pretty variable. It really depends on the product. And oftentimes disease pressure, they tend to work a little bit better in lower disease pressure situations. A big benefit, though, of these is that they have a very short pre-harvest interval. And resistance risk is not known. If you're interested in looking for more ratings of these different biologically based chemistries, you can find some of that in the up-to-date organic production IPM guide for grapes put out by Cornell, and the link is there for you. FRAC P are host plant defense induction chemistries. And so examples of these are Regalia, which I'm sure is a name we've heard a lot, as well as Lifeguard. And so you can see they both have different active ingredients, but what they do essentially is that when applied, they induce some type of systemic acquired resistance in the plant. Unfortunately, there is limited data on their efficacy. You can find some of that as well in the same production guide for grapes, the organic production guide. But again, they've got that caveat or benefit, I should say, of having that very short to 0 PHI. And there have been a few cases of resistance noted for phosphonates, which are in the FRAC-P group. Otherwise, for a lot of these other chemistries, it's unknown. And then this is for multiple groups. I just wanted to highlight this quickly because there are some newer chemistries that are powdery mildew specific chemistries. And so since we've got kind of the benefit with our cold climate grapes here, we tend to see resistance for other diseases. If you do tend to see more powdery mildew, there are chemistries that are specific to just powdery mildew. Now, if you have black rot and downy, they're not going to work towards those, but I think these are important chemistries to consider and potentially add into your rotations in future seasons. So some of the common ones are Quintec, Vivondo, and Torino. The U in front of that 8 and 6 for Vivondo and Torino denotes that the mode of action is unknown, so a U. Like I said, they're great for powdery mildew. They do have quite a variable pre-harvest interval. It really just depends on which product you've selected. And then the same rules apply. Don't use these back-to-back the same way you wouldn't use the FRAC 3s and 11s back-to-back. You really want to limit your application to about 2 per season. And the risk for resistance for these is medium. So in terms of kind of thinking about your plan for the rest of the season, starting with dormancy, the goal here is reducing that overwintering inoculum. And so you can use different few options for dormant sprays. I would say sulfur products tend to be the most popular. And the main target here, I would say, is anthracnose, but we do see efficacy for things like phomopsis and black rot with these dormant sprays. So preseason applications, unfortunately, don't really have an impact on powdery mildew, and that has to do a lot with the biology of the fungus. So you're much better to target powdery mildew once those buds have broken open and you're starting to see that green tissue emerge. That's when we want to target our efforts for powdery mildew. Now, a dormant season spray will not replace an in-season spray. This is just to help reduce that inoculum going into your growing season. So if you didn't have a problem with anthracnose or phomopsis or black rot, then you likely don't need to do this dormant spray. But this is an option if that's been an issue in your vineyard. So early season control, thinking Budbreak to the shoot elongation period. The goal here is really to protect those emerging green tissues, right? And so who loves those emerging green tissues? Phomopsis, downy mildew, and powdery mildew. And for that reason, those are going to be your big targets during this period. Hopefully by shoot elongation, anthracnose infection should be controlled. We try and recommend the multi-site chemistries at this point in the season, like your mancozeb, Captain, Xyram, and sulfurs, because they have that longer PHIs. This is a great time to use them. They're very effective, have broad efficacy, right? So you could use a mancozeb and hit a few birds with one stone with an application of that. And they're a really excellent resistance management tool because they're multi-site and not single-site fungicides. I have that little star by sulfur only to note that sometimes we have varieties that are sensitive to sulfur applications. So this is something to keep in mind. You're really going to want to try and save those single site FRAC 3, 7, and 11s till a little bit later in the season. So in the immediate pre-bloom to early bloom stages, this is a critical period for control, again, of downy mildew, powdery mildew, and black rot. This is a time of the year to bring your best products to your spray program. If you miss this spray period, it could make the rest of the season very difficult. This period coincides with a lot of spore dispersal and movement activity in the vineyard, so you really want to hit this period for your fungicide controls. Most sprays that you also select during this period will also have efficacy against phomopsis, which is great. Again, this is a great time to try and consider using a protectant and systemic. We didn't really talk about those terms so much, but it's kind of the example would be like having a multi-site in combination with a single site. So a nice example of this for early season would be Ridamil if you've had Ridamil Gold. If you've had really nasty downy mildew in the past and you've got another FRAC group in there for control of some of your other fungal issues. 1 to 2 weeks post-bloom, again, is another really critical period for fungicide sprays to control downy and powdery mildew, as well as black rot. And it's really the same information on this slide because the same information goes. So this is going to be a time in the growth stage of your grapes where they need a lot of this management for fungal diseases. So do I need a second post-bloom spray? It really depends. It's going to depend on the varieties that you grow, if you grow particularly susceptible varieties, but it's still a really important time for early season disease control. So I would say if conditions are really conducive or infections are present on the vines that you see during your scouting program, sprays might be needed. And again, some of what can assist with these decisions is using our NUA prediction risk models to try and determine if we're seeing conducive conditions or high periods of fungal infection. Resistant hybrids actually might not require the additional spray, but again, it's going to depend on the history of disease at your site. And so you know your site well, and you can make the decision as to whether that second post-boom spray will be needed. Even as fruits become resistant to infections, the foliage still remains susceptible. And this is something that we'll highlight in the next couple slides. So from bunch closer to veraison, our goal right now is protecting fruits and trying to mitigate those foliar infections. So at this point, you shouldn't really be worried about the black rot on the fruit or even hopefully too much powdery or downy on your fruit. You're kind of protecting them now from things like sour rot and botrytis bunch rot under conducive conditions. But your leaves can still very much get infected with downy mildew and powdery mildew. And if you've already had infections that haven't been well controlled up until this point, you will likely still need fungicides to prevent defoliation of the vines going into winter. So again, the critical control period for black rot, powdery mildew, and downy mildew has passed at this point. The foliage still needs to be protected. Of course, your pre-harvest interval is going to be a big limiting factor in the products that you can use at this point in the season because you are so close to harvest. So we don't really dive too deeply into botrytis and sour rot. I do acknowledge that these are things that we do occasionally see, but you have very similar options. So for for botrytis, you have FRAC 7 and 11 chemistries. But again, these are high risk for resistance, and your ability to use these safely is going to really depend on how you use these FRAC groups earlier in the season. Additional fungicides to consider would be something like Elevate, which is a FRAC 17, or Vanguard, which is a FRAC 9. Both are well rated for botrytis control. Sour rot control typically starts when you observe the flies around the fruit. So you're going to want to apply an insecticide plus oxidate, I think, is the current recommendation for controlling that kind of microbial fly complex. So the take-home message with all of this is that first, and Christelle really highlighted this well in the beginning of the talk, we are losing multi-site chemistries. And so this has led to the over-reliance on single-site chemistries. It's really important that you follow the rules for your pesticides of all selections, and acknowledge that this pesticide resistance approach is something that you have to be mindful of all season long. So during that dormant period is a great time to think about what worked and what didn't, and then how you're going to proceed for that following season. And chemistries, of course, are not the only available tool to control diseases and pests. And I realize the theme of our webinar right now is, of course, looking at these chemistries, but there are other cultural practices that can reduce pathogen pressure, pest pressure, and ultimately make your chemistries work a lot better. So the final thing I want to highlight before we get to your questions is on the site of multi-site fungicides, and your input is needed as a stakeholder. The EPA has issued a proposed interim decision for several multi-site fungicides. And so this is not a new thing that the EPA does. This is something that they do for different registrations of chemistries. And right now they're investigating several multi-site fungicides, including Xyram, which, as we've mentioned, is used on grape for control of things like black rot. And so your input is really valued. In fact, I've included a link that I will copy and paste in the chat here quickly. If I can find it. Where you can enter your comments as a stakeholder. Myself as a specialist, we also enter comments to try and prevent really the loss of these multi-site fungicides because they are such a critical tool for us. And if there's any questions about that, I'd be happy to answer them. And I think our last slide is just sharing some of the resources that both Christelle and I covered today. I wanted to highlight the fact that we do have apps like a FRAC app. I think there's an IRAC app where you can look at the different modes of action and educate yourself on what you're using. We also included information for Wisconsin's pesticide database in terms of what you're able to use in the state, as well as the different production guides. So this information will be available in the recording of this talk, and we can also put that in the chat. So I think we've left a few minutes for questions, and thank you all.
Thank you, Leslie. There was one question in the chat that I'm trying to go back to, but one question from Betty was, is post-bloom the same time as after bloom?
Yes, it is. Post-bloom, I think, is trying to signify immediately after bloom is over, and then after bloom can probably be pretty much all the time through the rest of the season. But post-bloom is just signifying that you don't want to get too far away from when bloom is ended before you're making that spray. And we typically say 1 to 2 weeks after bloom is ended is when you want that post-bloom spray on.
We have a question from David asking about why are these fungicides that you mentioned at the end being considered for discontinuation by EPA?
Yeah, thank you. That's a great question. So as I mentioned, these review periods happen every, I don't remember how many years that the EPA does them, but typically they come after various testing has been done on kind of like off or side effects or unanticipated effects of these chemistries on, could be marine life or other types of things. Even maximum residue limits has been a big issue for some chemistries. So they're typically seen, they've done tests that indicate that these fungicides or other chemistries have off-target effects that are concerning, and therefore they go under this review process to decide if they'll be continued as a registrant for on these different products. So, and it is unfortunate to see the multi-sites, which is really why I encourage our grape growers and other fruit crop production growers as well to make comment periods at that link that's open until I think the first week in April. So it's really valuable if you as a grower can make your comments. I'll also be making comments about trying to show the value and importance of these chemistries to our production.
Thanks, Leslie. While we're asking you to keep typing your questions, I will launch a poll right now that you can look at. Oh, the poll is launched already. Do you all see the poll? Because I don't see it.
I can see it.
Okay, good. Right. Thanks, Josie, for launching the poll.
If there's other questions, you can enter them into the chat or feel free to unmute yourself now that we're at the end of the presentation, if that's easier for you to ask your question.
And then also, please pay attention that the April 7th is going to be our herbicide selection webinar presented by Annie Claude, and that will be the last webinar from the grape series. So please make sure to join on that and register for this webinar. Any other questions? And thank you for answering the poll. Anybody else that would like to answer the poll? Leslie put in the chat the link to view the webinar recordings if you wanted to. There's also links for if there's anybody from Minnesota that will be, I forgot the name, but it's the something like small farm.
Yes.
I forgot the exact name.
I can pull that up right now, Christelle.
Oh, thank you, Leslie. But you can also see them there. They're the same webinar recordings. This is organized by University of Minnesota and really Annie Claude there and University of Wisconsin. So either one of them will have the same recording. Okay. Well, we only have 1 minute left. So we would like to thank everybody that came to this webinar. We're very appreciative of your attendance. And if you have any questions or anything, feel free to reach out to us. Thank you and have a good day.
Thanks, everyone.
Okay. Well, thanks, Leslie. That was great.
Yeah, thank you. That was good. It was a lot of information.
Yeah.